All right, it's the first Wednesday of the month, so we just had the sirens go off here. Just providing the setting for those at home. Hi, welcome to 11.3 Day 1. Today we're going to talk about independent, dependent events, and so now we're going to be working with multiple probabilities, multiple events happening. And so the first thing we have to talk about is what does it mean to be when the events are independent, okay? So the best illustration that we kind of use for this is, well, one of them is, I guess, pulling, like, let's just say, since I have this bucket here, markers out of a bucket, right? So in the bucket, we have, let's just simplify it, we have 5 red markers and 5 blue markers. Okay. And so let's say, what's the probability of somebody pulling out a marker and it being blue 2 times, right? So twice. Okay. Well, we have to be clear on if when we're pulling the marker out, oh, we can't pull all of them out. Let's see, let's ungroup this so it's more fun. All right, so when you pull the marker out, hello, there it's out, are we going to replace it before we do our second draw? And so this is that whole, you might remember this terminology, with replacement or without replacement. So if I don't put it back in there, then it's going to change the probability of the next time I pull a marker out of there, right? If I put it back in there, then it doesn't affect the probability of the second time I pull a marker out. So those would be then what we consider independent events. So events are going to be independent if the occurrence of one does not affect the probability of the other. And so this would be a case where we're doing a situation that's with replacement. Okay, so I have with replacement, and so therefore the probabilities are going to be, the second probability is unaffected by the first event happening, so they are, we consider independent events. So let's just say probability of blue and blue. All right, well, they're independent events, so that means the probability of, now let's just say blue 1 is A and blue 2 is B. So the probability of A happening is going to be 1/2, right? Times the probability of B happening, which is also 1/2. And so the probability of A times the probability of B is 1/2 times 1/2, which would be 1/4. So, there's kind of just a basic example of an independent event. You have with replacement, so you have replacement, so the probabilities are not affected. The second probability is not affected. So therefore, you can just multiply the probabilities together. So probability of pulling 2 blue markers out of there would be 1 in 4. All right. Any questions on that? Independent. Moving forward. A few different examples using dice. So let's say we're rolling 2 dice. Does the first die that we roll, the outcome on that die, affect the second outcome? It doesn't, right? Okay, so therefore the answer to this question is no. It's hard to see. And so therefore the events are still independent. And so if they're independent, then the probability of, let's just say rolling a 2 would be A, and rolling a 3 would be B, is equal to the probability of A times the probability of B. Right, so that would be the, I guess, the structure or formula for determining that probability. And so probability of rolling a 2 would be what? 1 out of 6, good. And the probability of rolling a 3 is also 1 out of 6. So this is 1/6 times 1/6, which is 1/36. Another way to think about that is just because this is a common sample space we've used, so we could just consider the sample space, and you might even be able to picture it without writing it out. But the sample space here would be like, I'm just going to write part of it. So like 1, 1, 1, 2, all the way over to 1, 6, right? Then this down here would be down to 6, 6. Okay, this one over here would be 6, 1, so on and so forth. And so there's 36 total outcomes in the sample space of rolling 2 die, right? So what outcome would be rolling a 2? Well, rolling a 2 would be this whole row right here, right? Well, actually it'd be more than that. Let's focus on where would be rolling a 2 and then a 3. What would that look like? That would be right here, wouldn't it? How many outcomes are rolling a 2 and then a 3 out of the 36? 1. A 3 and a 2 would be different. So rolling a 2 and then a 3 would have one outcome. It's right there, and it's the 1 out of 36 outcomes. And when you calculate the probability using the independent multiplication of the 2 separately, you get the same thing, 1 out of 36. So I guess what I'm trying to say is sometimes you might be able to look at a picture and say, oh, well, that's rolling a 2 and then a 3, that's 1 out of 36. All right, but some of the questions that you might see or something in like a higher level stats class might require it's a more complicated sample space, and so you might rely on just using like the structure of probability of the A happening times the probability of B happening. It might be a little more complicated than just some simple little happy math book problem. But another happy math book problem, probability of 4 and then an even number. Are these two events independent? I think so. So probably if A is a 4 and B is even. So what's the probability? That would have been a good soundbite, Ash, right there. Probability of A would be, probability of rolling a 4 would be 1/6 again. Probability of an even number is 1/2. So 1/6 times a half is a 12th. That's right. That's right. Yep. And if you think about it, 1/12 is 3/36. So what 3 outcomes in the sample space would satisfy that? 4, 2, 4, 4, and 4, 6, right? Since we know the sample space. So you can kind of see it in the picture, and you can see how it's calculated as well. All right, moving on. Here's another problem very similar to that problem, but a little different number cube or die. So 6-sided cube has a 1, then a 2, 2, and then a 3, 3, 3. Crazy die. Crazy die. For a crazy guy. All right, 4 sides are colored, 4 with red, and then 1 with white, 1 with yellow. Find the probability of rolling a 2 and then another 2. Well, rolling a 2, they're independent, don't you think? Don't you think, class?
Yes, sir. Yes.
All right, so rolling a 2, good. Yes, sensei. Rolling a 2 is 1. Wait, rolling a 2, how many 2s? Yeah, there's 2, 6, so it's 1/3. And then rolling another one is 1/3 again, so that would be the product equal to 1/9. Rolling a red, and then a white, and then a 1. This is 3 events, right? So this would be like the same thing for 3 events. If they're all independent, probability of A times the probability of B times the probability of C. So the probability of A is going to be 4/6, which is 2/3. Probability of getting a white side is 1/6, I believe. and the probability of a 1 is also 1/6. So finding the product of those, I would, I would simplify before you multiply there. But everything's all simplified, isn't it? Except for 2/3. So take 2/3, I'd take that, I'd go chop that 2 with one of those, and then I'd have a 1/54. Neat. Okay, that's independent probabilities. Okay, the next slide is talking about the other side of that when they're dependent. So now, if I'm talking about the old bucket problem, I was talking about markers in a bucket, all right, and I have my markers in the bucket, and there's 5 blue ones, 1, 2, 3, 4, 5, and there's 5 red ones, 1, 2, 3, 4, 5. This is a situation now where we are not replacing. It's without replacement. And so if you don't replace the marker in the bucket, it affects the second probability because there's one less marker in there. Okay, so if I want to know the probability of blue and blue again, and they're dependent and they're without replacement, it's going to be slightly different than what we saw before. The probability of blue is going to be 5/10, which is 1/2, right? So it's still 1/2 times, now this second part right here, this B and then the vertical line A, what that means is the probability of B given A happened. So whatever event A is, it happened. So now we have to determine and tweak or change our probability of that second event because it's changed now. So the probability of B given that A happened is going to be what? If I already pulled a blue marker out, then what do I have left? Here, let's just pull one of these blue ones out. Geez, you're all grouped together there, you groupies. Excuse me. So I pull a blue one out. Yeehaw! Yeehaw! Put all them red ones back in there. Now how many markers do I have in there? How many blues? 9. No, how many blues? 4 out of a total of 9, so it's a slightly different probability now. Now it's going to be 4/18, which is the same as 2/9. So that's dependent. That's going to be an example of a dependent probability, okay? Because this first outcome affected the second. So back to rolling dice, back to gambling and rolling dice, you guys. All right, here we go. You got to ask yourself, is it independent or dependent? So in this case, the event is rolling 2 standard numbered cubes. The first die shows a 2, and the sum of the 2 dice is less than 8. So if the first die is a 2, does that affect the probability of the sum being less than 8? Yeah, it does. So these are actually dependent. So you got to be a little careful. You can't just go automatically number cubes, rolling number cubes. No, those are independent. It depends what you're asking. Okay. So in this case, what's the probability of the first die showing a 2? We'll call that A. And the sum of the 2 die less than 8, we'll call that B. The probability of A is going to be 6/36 or 1/6. And the probability of B given that A happened. Well, if A happened, that means that the first die is a 2. That means I'm right in here. Right? I'm one of those 6. Agree? So if that happened, now what's the probability the sum is less than 8? Well, that one is, that one is, that one is, that one is, and that one is. Okay, so given that A happened, the probability of having a sum less than 8 is going to be 5/6. getting to that. I just did the probability of B given A. So now the probability of both of them happening is the product of the two. And so the product of the two now is going to be 1/6 times 5/6. Okay, so the probability you roll 2 dice and the first one's a 2 and the sum is less than 8 is going to be the product of 1/6 and 5/6, which is 5/36. And like I told you earlier, sometimes if the sample space is simple enough, you can just look at the sample space and go, yep, there's the 5 cases for when that happens, right? Out of all the possible 36 outcomes. Okay, but sometimes the probability isn't as simple as just rolling 2 dice, so we have to have this type of a structure to calculate these probabilities. Like actual, if you're really actually calculating probabilities of something real. Like, what's the probability that it's going to snow given that the temperature is going to be, or something like that. And there's all these little models that they have. They plug in all this data and they collect all this data and they run all these things and then they tell you that and you interpret the. So, I mean, obviously real things are a lot more complicated. Okay. First die shows a multiple of 3 and their sum is 7. So this is just another example of these types of probabilities here. First die shows a multiple of 3. What's the probability of that? Okay, that would be my A. And multiple of 3. So that would be, what are multiples of 3? 3 or 6? So let me erase this crust up here. So the first, so that would be in, hello, that would be first die shows a multiple of 3 would be that row or this row, correct? And their sum is 7. So now this just narrowed down a bunch of the sums of 7 because 5 and 2 is not one of the possibilities here. So these are going to be dependent events. It's changed. For both, you know, if probability of A and the probability of multiple of 3 and their sum is 7, well, being a multiple of 3 limits having a sum of 7 because this one is not going to be possible anymore. Neither is that one, neither is that one, and neither is that one. So it's limiting our options to have a sum of 7. So the probabilities are going to be dependent. Okay, so the probability of showing a multiple of 3 is going to be 12 out of 36. So whatever that is when you reduce it, right, that's going to be what, 1/3. So it's better to reduce before you end up multiplying stuff. So 1/3. And then the probability of B given that A happens. So how many of these have a sum of 7? 1, 2. So 2 out of 6, which is 1/6. And so the total is going to be the 2 green ones you see in the end. After you multiply 1/3 times 1/6, you're going to get 1/18. And 1/18 is equivalent to 2/36. And the 2/36 you see circled in green up here are the 2 possibilities. So again, you could just have the sample space and look at it and answer the question, and that would be fine with me. But also understanding how you calculate things is important when it gets to be more confusing. All right. I think this next question is just another similar type of question, so I'm going to skip over that for sake of time. This one is one for you guys to try on your own. So I will put the answer key up to that in 5 seconds, so you can pause it and try it on your own, and then you can check. 5, 4, 3, 2, 1. Okay, if you did those problems, here are the answers for those. And then the last page, we're talking about doing some drawing of cards from a deck. So determine whether the events are independent or dependent. Probability Queen of Diamonds replaced, then an ace is drawn. So here's this replaced business. If it's replaced, then we're talking about being independent. So you can just multiply those probabilities of those two events happening separately. So the probability of a Queen of Diamonds is going to be 1 in 52. And the probability of an ace that's drawn is going to be 1 in 13. And so the probability of having both a Queen of Diamonds and an ace when you replace it is the product of those two together, which whatever 52 times 13 is, that would end up being 676. So 1 out of 676. Next one, probability of selecting two hearts with replacement. Okay, so with replacement, again, you're replacing it, so it's going to be independent. So we'll be able to multiply those probabilities together separately. Selecting two hearts would mean selecting one heart would be 1/4 of the deck is hearts, and the another one would be another fourth. So 1/4 times a fourth is a 16th. All right, probability of selecting two hearts without replacement. Now this gets a little more interesting. Without replacement means that we're talking about dependent probabilities. And so the second draw is going to be slightly different because we did not replace the first one. So the probability of A times the probability of B given A happened is going to be the probability of drawing one heart would be just like before, 1/4, but the probability of drawing another heart given a heart's already gone is going to be not 1/4, but 12 out of 51. So there's one less card, so it's not out of 52, and there's one less heart, so it's not 13. So the one before would have been 13 out of 52, which is equivalent to 1/4. So we have 1/4 times 12 51st. That's going to have some canceling. And so the 12 and the 4 cancel out, leaving a 3. So that's going to be 3 out of 51. Okay. And then the probability of a queen not replaced again. So a queen drawn and then a king drawn. Well, queen drawn, that's going to be the probability of A times the probability of B given A happened. So probability of one queen is going to be 1/13th. And the probability of a king, there's still 4 kings left, given that a queen was drawn. So that would be 4 out of 51. So that's going to be 4 out of whatever 51. Let's see here. 13 times 51. 663. Okay. So that is the whole independent dependent day 1 lesson. There's your homework assignment, and happy state tournament weekend, everybody.